Okay, let's look at section 7.4. We're going to be adding and subtracting and multiplying radical expressions. They look an awful lot harder than they really are. You just got to remember some of the basic rules that we learned in our last session. So, like radicals is the big thing we're going to have before we add them. So if we have two radicals, they are like, and hence we can add them if they have two things have to happen. They have to have the same index in and the same radicand. Remember, radicand is another word for the number under the radical. So let's look at this. Let's look at some examples before we actually do some work. Like radicals. So for two radicals to be alike, they have to have both conditions met. The same index, and translating to my preferred language, same expression or number under the radical sign. So let's look at 3 or 4 examples. The square root of 7 and the square root of 8. Now remember, the square root has index 2. These have the same index, but the number under the radical sign is not the same. So these are not like radicals. So let's look at another example. What about the cube root of 5x squared and 7 times the cube root of 5x squared. So notice, remember, this is just your regular 7, like 1, 2, 3, 4, 5, 6, 7, and it's multiplied by this. So we're just only caring about whether the radical itself is like. So we're looking at this, and we're looking at this. We see that they are both index 3, and that the expression under the radical is the same. So these are like radicals. And finally, one last example before we do some exercises. Let's look at the square root of 31xy and the cube root of 31xy. And here, if we literally look at this, we will see at the very first that they don't have the same index. So I'm done. They're not like. Okay, with that in mind, let's use that to add and subtract like radicals. So when you're adding and subtracting like radicals, it's just like you are adding and subtracting like terms. You just treat the radical like it was an x term. It's some unknown, and you just add the coefficients. So this is example 1a. So we have 4 on the square root of 11 plus 8 on the square root of 11. So these are like radicals because they're both square roots and the number 11 under the radical is the same. So this is equal to 4 plus 8 times the square root of 11. Notice all I'm doing is I'm adding the coefficients, which is equal to 12 on the square root of 11. Of course, I hope you can anticipate that we're not always going to be given such simple problems. Sometimes we will have to use transformations to make our radicals like. But not for these first examples. So we have 5 times the index is 3, so the cube root of 3x minus 7, index 3, which is the same as the cube root of 3x. So my radicals are like, so I just treat them as a unit, and I just take the coefficients, the multiples. They're really not called coefficients, but they're so similar, you can think of them that way. We just call them multiples. So we take their multiples, 5 minus 7, and we multiply that by the radical, and we get minus 2 times 3 on the square root of 3x. So let me help you here, if I can. So I don't know, and we're assuming all of our values of x are such that these make sense. In this case, x can be any number. So I don't know what this value is, and I can't evaluate it because I don't know what x is. But I know it's something, so I might as well call it m. Well, if m is equal to the cube root of 3x, then over here, the cube root of 3x is also equal to m. So this becomes 5 times m minus 7 times m, which is equal to minus 2m, which is equal to minus 2. And what is m? My m is the cube root of 3x. So really that's all we're doing. We're just treating this whole glob of something as an unknown. So if you want to do it that way, conceptually I would suggest only for you to kind of get a better feeling, because that just looks nasty for people who don't like math. But it really isn't. It's just some number. We cannot tell you exactly what that number is because we don't know the value x, so let's just call it m. It is something, and I designate it as m. You can choose x or y or z or whatever variable you wish. So this is number 1c. We have 4 times, notice that the second root of 5 is just the same as over here. We don't normally write the index, but we did this time. This is the same as the square root of 5. And we want to add it to 4 on the cube root of 5. Well, no simplification is possible because these are not like radicals. While it's true that the numbers under the radicals are the same, the indices, and that's the reason they're written here, 2 and 3 are not the same. So basically, it's some number, but I cannot simplify the number algebraically because they are not like radicals. Okay. So again, they assume all variables represent positive real numbers, and that's just to make sure that everything is actually a real number. Of course, in number 2a, there are no variables, so there's nothing to assume. So I have the square root of 20 plus 2 on the square root of 45. So right offhand, they don't seem like they're like radicals, but we might be able to transform them into like radicals. So what we do is we do a factor tree for 20 and a factor tree for 45. So 20 is divided by 2. 20 divided by 2 is 10. When they're even, I just divide them by 2. 10 divided by 2 is 5. So that means 20 is equal to 2 squared times 5. Why 2? Because these are our primes right here. When we get to a point where a number cannot be divided by any other number besides itself, it's a prime. So let's do the same thing for 40. So 40 divided by 2 is 20. Oh, that makes it easy. So 40 is equal to 2 times 20, which is equal to 2, because right over here I have the factorization of 20 times 2 squared times 5. So all I'm doing is multiplying out, so that's equal to 2 cubed times 5. Oh, well, that's 40. That's not doing me any good. We need to do 45. So, sorry. Well, it wasn't completely wasted because we immediately saw that 20 was a factor and already figured it out. But of course, this is 45, and that's what we need to do. So, you just divide through by the obvious thing that you get. So 45 is obviously divisible by 5. So that's 45 divided by 5 is 9. And 9 is 3 times 3. Or 9 divided by 3 is 3. So here are the primes. So 45 is equal to 3 squared. Because that's 3 times 3 is 3 squared times 5. So we're going to use these factorizations over here. I'm going to write the square root of 20 is 2 squared times 5. And then I'm going to write the square root of 45 is 3 squared times 5. Now, whenever you have a perfect square, so remember, again, we don't write the indices, but it's important that you understand that when we're doing the square root of 2, the index is 2. So here, this is 2 squared, the square root of 2, and this is 3 squared times the square root of 3. So let me just show you this whole thing, because I'm taking shortcuts here, but I think it's important you see it. So let's do this one. The square root of 2 squared times 5 by an operation we learned last week. That's the same thing as the square root of 2 squared times the square root of 5. But the square root of 2 squared is 2 times the square root of 5. So what we're doing is whenever we find something under a radical that's raised to a power that's the same as the index, then the base can be taken out and put at the front. So the square root of 2 squared times 5 is 2 times the square root of 5. So if you need to, just go back to this. Erase that. And this is being added to 2. So the square root of 3 is going to come out. So it's going to be 2 times 3 times the square root of 5. Just to make sure you understand that, let's look at this right here. This is 2 times the square root of 3 squared times 5. So that's equal to 2 times the square root of 3 squared times the square root of 5. But the square root of 3 squared is 3. So that's 2 times 3 times the square root of 5, which is equal to 6 times the square root of 5. So this whole thing becomes 2 on the square root of 5 plus 6 on the square root of 5. So you can see by transformations I was actually able to arrive at like radicals. So this is just equal to 2 plus 6. I add together the multiples times the square root of 5. So the answer is 8 on the square root of 5. So our next one is, let's pull this down, this is example 2C. Again, even if we were meeting in the classroom for most of chapter 7, I'm going to keep things basic. But when I say I'm going to keep things basic, it doesn't mean, oh, I don't have to worry about it. It means you have to understand the most basic application of all of the rules. And you're going to be getting a lot of the rules. And you have to remember those rules in the most basic application. I'm not going to throw you any really hairy ones, although we may do some that you consider complex as exercises. But on the next exam, whether it is in my math lab, Canvas, both, or just one of those two. So this is the square root. So all of these are the square roots. So what I want to do is I want to factor 27. 27 is divisible by 3. How do I know it's divisible by 3? Here's a divisibility check. If the digits add up to a number that is divisible by 3, then the number itself is divisible by 3. So 2 plus 7 is equal to 9, and 9 is divisible by 3. So 27 divided by 3 is 9, and 9 is 3 times 3. So if you don't remember from our list of cubes and everything else, 27 is 3 cubed. 9x is 9 is equal to 3 squared, and 72 is equal to, well, do we have 72? Well, let's divide it by, where's my eraser? So let's do a factor tree for 72. So you may immediately realize that 72 is divisible, is the same as 9 times 8. But 9 is 3 times 3, and 8 is 2 times 4, which is 2 times 2. So 72 is equal to so here are my 3's. Let's do with my 2's first. Start with the smallest. Is equal to 2 cubed times, and now I have two 3's, 3 squared. So we're going to come back over here and we're going to replace 27 with 3 squared times, 3 to the third times x, minus 2 times 3 squared times x, and 72 is 2 cubed times 3 squared times x. So let's go ahead and continue down. This is going to be one you're not going to get on an exam. So if you think about this, I want to have a like radical. And is it going to be possible? Well, let's just do what we can do. Let's write, this is 3 squared times 3 times x. I can already bring 3 out. So this is going to be 2 times 3 times the square root of x. And this is going to be 3. I'm going to bring out the 3 times 2 cubed on the square root of x. Well, let's continue on. So 3 squared can be brought out. So remember, I've written 3 cubed is 3 squared times 3 times x. So this is going to be 3 times the square root. I don't really like this particular example, but let's go ahead and do it. 6 on the square root of x and plus 3, and over here I'm going to write 2 cubed is 2 squared times 2 times x. So this is 3, the cube root of 3x, minus 6 on the square root of x, and here I can bring out the 2, so this is 3 times 2 times the square root of 2x. So I'm not going to be able to transform this into a like radical. It's literally going to stay in this form, but it is simplified somewhat. Don't really like that one, but that turns out to be the answer. Again, I reiterate, I will not give you one like that in real life. And indeed, sometimes I question why they gave us this one, because we all realize by now that the examples they give us are chosen specifically to be examples where we can use our rules. And the only rule we really used here had nothing to do with actually finding a like radical. So that's it, and we're going to move on. So this is example. Yeah, I've actually, I think I'll go when after this is over, I'll just remove that example altogether from the notes. I've actually already gone through these and removed some examples already. Because this chapter we want to keep basic. So this is 2b right here. So we have the cube root of 54 minus 5 on the cube root of 16 plus the cube root of 2. So my only hope is to, if I'm going to add these, is to express these somehow as the cube root of 2. So clearly, since 2 is prime, I cannot do anything with this expression right here. It's as simplified as I can be. So let's go ahead and let's take 16 and make its factored tree. So 16 turns out to be 2 times 2 times 2 times 2. It's equal to 2 to the 4th, which is equal to 2 squared squared. And let's do the same thing with 54. 54, we're going to divide it by 2, and that's going to give me 27, right? Yep. 27 is 3 times 9, which is 3 times 3. So 54 is 2 times 3 cubed. So let's take the cube root of 2 times 3 cubed minus 5 times the cube root of, we don't want to write it this way, let's just leave it, I was thinking they were square roots, of 2 to the 4th plus, well, here's the trick we did last time. So this is going to be an easy simplification. Since the index 3 and the power 3 are the same, I can bring the base 3 out from underneath the radical. And what is left is the square root of 2. Here is the trick that we did last time. Index is 3, so I want to write 2 is a power of 3 times 2. So 2 cubed, so 2 to the 4th is 2 to the 3rd times 2 to the 1st. Now I have matching indices. So let's go ahead and simplify. This is cube root of 2 minus 5. So I can take out the base 2 because they're raised to the same power. But this one, the square root of the single 2 raised to the first power, stays behind. And then, like I said, there's nothing that can be done about this last one. So this gives me 3 on the square cube root. These are all cube roots, sorry. Cube root, cube root. Cube root 2 minus 10 on the cube root of 2 plus 3 on the cube root of 2. So now I've actually were able to transform them all so that they all have the same like radicals. So this is equal to take the multiples 3 minus 10, and this is the same as 1 times that plus 1 times the cube root of 2, and I get 3 minus 10 is minus 7 plus 1 is minus 6 cube root of 2. So let me go back really fast. This is this right here. I want to show you because I have a feeling somehow this may have lost you, and some of you are feeling a bit so let's just look at this line right here. And I'm going to say let m equal to the cube root of 2. So this becomes 3 times the cube root of 2 is 3m. This is minus 10 times the cube root of 2. So it's minus 10m. And let me erase that 1 that I put right there. And this is plus m. And none of you should have any problems figuring out what 3m minus 10m plus m is. That's the same as 4m minus 10m, which is the same as minus 6m. But I let m equal to the cube root of 2, so that's minus 6 times the cube root of 2. Okay, number D. So this one's example 2D. So again, we have a cube root. The cube root of 48y to the 4th plus the cube root of 6y to the 4th. So let's go ahead and factor our 48. 48 divided by 2 is equal to 24. Divided by 2 is 12. Divided by 2 is 6. Divided by 2 is 3. So here are all of our primes. So 48 is equal to 2. How many of them? 1, 2, 3, 4. Raised to the 4th power times 3. 6 is easy. We already have it right there. It's equal to 2 times 3. So I'm going to want to do something here. I'm going to write 48 with 6 as a factor. So I'm going to split 2 to the 4th is 2 to the 3rd times 2. And then I have it times 3. And why do I want to do that? Because this is a cube root. And y to the 4th, for the same thing, I want to write as y cubed times y. I want to get a cube in there. So let's do that. 48 I'm going to write is 2 cubed times 6. We can keep this as 6, that's fine. Times y cubed times y. Plus the cube root of 6 times y cubed times y. So let's lump together all of our cubes. This is 2 cubed times y cubed times 6y. And here, y cubed times 6 times y. So now, since these both have, these are cube roots here, since both of these have the same exponent as the index, I can bring them out. 6y has to stay underneath there. Y cubed can be brought out as y, just the bases. If you can think, it's like the indices cancel. The power in the index cancels. And it's over 6y. So I can actually add those. So 2y times the square root of 6y plus y. What I do is I add the multiples, 2y plus y times cubes, these are cube roots of 6y. So the final answer is 3y times the cube root of 6y. You can over here let m equal to the cube root of 6y and rewrite this as 2y times m plus y times m, and that's 3y times m, but m is equal to the cube root of 6y. Okay, that's the addition of radicals. So we actually have two others, and they're fractional powers, and you should watch this. These aren't as bad as you think they're going to be. I would have kept these two in. So this is example 3. The book is full of examples. So the square root of 45 over 4 minus the square root of 5 over 3. So clearly I'm going to have to add these at some point, and the LCD of 4 and 3. Well, if we use the third property of LCDs, the LCD of two numbers is always greater than or equal to the larger of the two numbers, and it's equal to the product of the two numbers if those two numbers share no common factors. And 4 and 3 share no common factors, so the LCD is equal to 4 times 3, which is equal to 12. So that's one preliminary. I'm going to need the LCD. But I'm going to factor 45. Well, 45 is 9 times 5, and 9 is 3 times 3. So 45 is 3 squared times 5. So let's go ahead and rewrite that. Notice my index here, it's unwritten, but it's 2. So that's 3 squared times 5 over 4 minus the square root of 5 over 3. Let's go ahead and simplify up here. Since the index, the unwritten index, is 2, that means I can bring the base 3 out. The 5 has to stay underneath. This is 4. This is 3. So now is the time to use my LCD. My LCD was found to be 12. 12 divided by 4 is 3. 3 times the numerator is 9 on the square root of 5. 3 times 3 on the square root of 5 is equal to 3 times 3 times the square root of 5 is 9 on the square root of 5. That's how I got that. Now 12 divided by 3 is 4, and 4 times minus the square root of 5 is minus 4 the square root of 5. So now I can actually, if you look at my numerator, those are like radicals. So 9 minus 4 is 5. And we're done with that one. B looks hideous. Looks that way. It actually does not turn out to be. Just which one is this? Number 3B. So the cube root, when they look really bad, there's usually some trick. that makes them really easy. So I'm going to use the quotient rule for radicals here. Remember the quotient rule for radicals says the nth root of a divided by b is the same thing as the nth root of a divided by the nth root of b. That's the quotient rule for radicals. So I'm going to use it right here, and I'm going to simplify all of this as the cube root of 7x over the cube root of 8 plus 2 on the cube root of 7x. I'm going to go ahead and make that into a fraction because eventually we're going to have to add them. But let's factor 8. 8 is 2, 4, 2, 2 is equal to 2 cubed. So writing that down, it's the cube root of 7x over the cube root of 2 cubed. That's kind of nice. Plus 2 times the cube root of 7x over 1. I'm going to erase this stuff over here because I'm just going to write right on over there. Well, this is equal to the cube root. The denominator cannot be simplified. But the cube root of 2 cubed is just 2 plus 2 over the cube root of 7x over 1. So now my LCD is 2. So all of this is the LCD of 2. In other words, the LCD of 2 and 1 is equal to 2. They don't share any common factors. Multiply them together. So 2 divided by 2 is 1, and 1 times the numerator is just that numerator. 2 divided by 1 is 2, and 2 times the numerator is 4 times the cube root of 7x. So now, as before, I can just add these. So that's 1 plus 4 times the cube root of 7x over 2, which is equal to 5 on the cube root of 7x, all of which is over 2. So enough of adding, right? You hate anything with adding fractions. Listen, I find it almost incomprehensible that people are graduating high school without knowing how to deal with fractions, adding them and subtracting them, that they literally get out a calculator. It's a skill you need to know. And it's also one of those skills that UCF has told us we need to absolutely emphasize. So if you're planning on going, and I'm hoping all of you are, but of course some of you won't, it doesn't fit with what you want to do with life. But if you go to a 4-year university, they're going to expect you to know how to add and subtract fractions. So here, let's recall the following rule. If the nth root of a and the nth root of b are real numbers, then the nth root of a times the nth root of b is the nth root of a times b. So that's all we're going to do. We're literally going to use that rule, and we're going to do the multiplications. These aren't so bad. This is, I guess, example 4. So I definitely skip around on these examples. So the square root of 3 times 5 plus the square root of 30. Well, we're just going to use distribution, right? So that's equal to, when I multiply a whole number times the square root, it's customary that we put the whole number in the front. And the square root of 3 times the square root of 20, using the rule, they're both real numbers, is the square root of 3. I said the square root of 20, I meant to say the square root of 30. 3 times the square root of 3 times 30. So let's simplify that. That's 5 square root of 3 plus the square root of 90. So let's look at 90. Well, the obvious thing is it's 9 times 10, and 9 is equal to 3 times 3, and 10 is equal to 2 times 5. So the only thing that we can do here to simplify this, because these are index 2, since there's no squares, you could have just left that 3 squared times 10, and that's what I'm going to do, because the only thing I care about are the things that are perfect squares. Can't do anything to simplify that first term, but here I can pull out the 3. And that is it. It cannot be simplified beyond that point. Now let's do 4c. So we're multiplying 7 times the square root of x plus 5 times 3 on the square root of x minus the square root of 5. So if you did not recently download your sheets, you might have something different for number C. I noticed that the book had the square root of 5. I think earlier I just had 5. I wanted it to be 5, but the book has the square root of 5, and I want to go with what the book does, because you can always look at your e-text and look at these examples. So I'm multiplying two things. So I'm going to take the first 7 square root of x and multiply it by the entire second factor, which is 3 on the square root of x minus the square root of 5. And then I'm going to take my second term in my first factor together with its sign and multiply it by the entire second factor again. So I'm just using distribution twice. Now let's multiply these out. So this is 7 times 3, and the square root of x times the square root of x. So this is the square root of x squared. Then 7 times the square root. So this is 7 times minus 1. There's an unwritten minus 1 there. So this is 7 times minus 1. So that's minus 7. And the square root of x times the square root of 5 by our rule is the square root of 5x. So I've completed this first grouping. Now let's go to the second. So this is 5 times 3, which is 15, times the square root of x. And this is 5 times minus 1, which is minus 5, times the square root of 5. So is there anything that we can do to simplify? There's only one thing, because these are not like radicals. Right here, this is not like radicals. This is just a number, so it can't be simplified. But the square root of x squared is the same as the square root of x squared, which is equal to x. We don't need the absolute value because we already know it's positive. The square root of x is always a positive number, and a positive number squared, or any number squared, is positive. So this first turns out to be 21x minus 7 times the square root of 5x plus 15 on the square root of x minus 5 on the square root of 5. And I can anticipate your panic out there a little bit, somewhat maybe. And so, of course, some of it I will have no idea. Is you're wondering, how the heck do I know when I'm finished? How do you know? Because this is new to you. How do you know that that cannot be further simplified? And the answer to that is you're going to hate is practice. And that practice involves doing a lot of examples for which you have the correct answer. And again, for that reason, everything on your Canvas exam, and that may be the only exam that you get on Chapter 7, will be really basic applications that will not require you to wonder, have I missed something? Is there something I could do to simplify this? And there's not. 5 is prime and x is prime, so there's nothing you can do to simplify those. Minus 5 times the square root of 5, that's prime, can't simplify it. So again, a radical of index n, hopefully this will help you somewhat, is fully simplified when all factors of, and here I'm going to use the word I hate, the radicand, because it's shorter. That's just the expression under the radical to the nth power are removed. And by removed, it's removed from underneath the radical. Okay, moving on. I think we have 2 more problems. Yeah, we just did that one. So we're going to do E and F, and that'll be it. And like I said, I've already removed several problems from this list. They give you an awful lot of examples, and again, it's the book realizing in order to get a feel of this, you need a lot of examples. But you're learning this at home under non-ideal conditions, and even if we were learning it in the classroom, I would keep the examples really simple. Now these two last examples, these are examples that you want to pay attention to, because these are examples of things that put a lot of stuff we've learned together, and when we put a lot of stuff that we've learned in the past to make something easy, then we want to use it. And both of these examples are going to be turn out to be very easy. The key to example 4E is to remember that A minus B times A plus B is equal to A squared minus B squared, where A and B are anything. They can be polynomial terms, they can be algebraic expressions, or they can just be real numbers. Because in the end, they all boil down to real numbers, right? Even if it's an expression like 2x, x is going to be some real number. No matter what it turns out to be, it's going to be another real number. And 2 times a real number is a real number. So here we have the square root of 2x minus 5 times the square root of 2x plus 5. So you notice these are two terms, and the terms differ by sign. So A minus B times A plus B is equal to A squared minus B squared. Well, A is simply 2x, and B is just 5. So that gives us, using the formula, and that's exactly what we want to use. This is something we've learned in the past. 2x squared minus 5 squared. And the square root of 2x squared is just 2x. And I'm subtracting from it 5 squared, which is 25. So that was pretty painless. No multiplying out using distribution or anything. And we're going to do the same with number f. 4f. So we have a formula for squaring, just like we do for a plus b squared. Well, that's equal to a squared plus 2ab plus b squared. And just like before, a and b can be terms of a polynomial, algebraic expressions, or real numbers. And that's what we're going to have now as an algebraic expression. I have the square root of x minus 3 plus 5 squared. So study these, you'll see them again. So let's compare that with a plus b squared. It's equal to a squared plus 2ab plus b squared. Well, my a is equal to x minus 3, and that's squared. And then 2 times ab, or if we need to, that's the same as 2ba, same exact thing. So this is going to be 2 times my b is 5 times my a is the square root of x minus 3. And b squared, b is equal to 5. So, just to make sure you see what's going on here, this is a squared plus 2ba plus b squared. That's how I'm getting that. So now it's just the simplification step. So x, the square root of x minus 3 squared is equal to x minus 3. 2 times 5 is 10 times the square root of x minus 3. And 5 squared is 25. So the only thing I can do is collect like terms, and the only like terms here are the minus 3 and the 25. So this is equal to x plus 10 on the square root of x minus 3 plus 25 minus 3. Those are my two like terms. So the final simplification is x plus 10 on the square root of x minus 3 plus 22. And that's it for 7.4.